Free falling from space. Welcome to practice number 157. Today we're talking about how skydiving from really high, like 40 kilometers high, affects your aerodynamics. And this is interesting because back on October 14th, 2012, a geezer named Felix Baumgarten set the world record for fastest free fall jump, which he set from 39 kilometers high. And at the time, this was also the highest jump in history. So he fell so fast that he broke the sound barrier and there was this shock on his head. Now, a shock on your head would put so much pressure on your neck, and I thought that maybe Felix would have had a really huge neck. So I looked up one of his pictures, but it turns out he just has a normal size head. A normal size neck as well. So they say that he had a suit on, so maybe the suit took some of the force. Or the theory I like is that because it's the funniest, is that maybe they loaded a dummy into the suit and just threw that out of the window instead. So another thing about the jump that doesn't really make sense is that he fell faster, and quite a lot faster, than aerodynamic theory predicted. And to look into why, we are looking at this paper called Aerodynamics of a Highly Irregular Body at Transonic Speeds, Analysis of Stratos Flight Data. So you can find this paper in the link in the description. It's open access, so you can find it easily for yourself. And there are a lot of factors that need to be considered if you want to accurately calculate how fast something will freefall, particularly from really high up. One major difficulty is the temperature changes throughout the troposphere, which is the part that we enjoy living in. The temperature change through this troposphere is approximately linear, but even that linear change affects the density of the air. So that has to be taken into account as well. And things become even more complex when you factor in the effect of the Mach number. So the Mach number is very important once you start reaching the sound barrier, because the air in front of you starts to become really squished and it can't move out of the way fast enough. This then leads to shock waves forming. These shock waves are nothing other than just all this air being compressed together. So you're like trying to punch through it and it's just like this invisible wall kind of thing. So with this, as you can probably imagine, comes an increase in the drag coefficient because there's this pressure pushing back on you. And this drag coefficient is quite difficult to predict when you're just looking at the Mach number. But when you couple the temperature changes and the changing conditions such as the angle of attack and the density of air and all those kinds of things, free falling from 40 kilometers high almost, it is currently effectively impossible, although many have tried to calculate it, to calculate what the drag coefficient is, for example, and what speed you'll be reaching. And some have come very close to having decent predictions, but not perfect predictions. And one additional parameter that is important at high speeds is something called the Knudsen number. So Knudsen number. What this number tells us is whether the air or the fluid in general acts in a continuum fashion or not. So what this means is, in English, is that if the Knudsen number is low, the air can be treated as we normally would think of it. But if it is high, then it means that the air acts more like individual molecules than one general mass. With that, one notable change is that the medium effectively becomes a slip condition, meaning that the molecules just slide past each other without any real resistance. Fortunately for this jumper, he was still within the stratosphere when he jumped, and so the Knudsen number was within continuum limits, which means that the conventional aerodynamic equations can still be used. If you went higher, then potentially even these would break down. So that doesn't mean that these equations are accurate necessarily, because there are other factors that need to be considered, like the Mach number, as we previously discussed, and we'll discuss more of these in this paper. And one more interesting thing to note is that when you're looking at how fast something will free fall from a really high altitude, we actually have to take into account Earth's rotation, because this creates a centrifugal force on the jumper as well, thereby changing his or her trajectory and acceleration. So the authors of this paper did a lot of math to try to derive some models to predict how fast this guy Felix fell. They have real-life data as well from the jump that actually happened to compare to these models to determine what's accurate or not. So let's look at how fast Felix actually fell. And one thing to note is that old boy Felix was wearing a pressure suit, so that will change his shape a little from the basic human form. And they say that, if we scroll down a little bit, that Felix jumped from the capsule at a height of 38,969 meters. That's really high. At 50 seconds into flight at an altitude of 28,833 meters, he obtained his maximum vertical velocity of 377.1 meters per second, equaling Mach 1.25. His free fall lasted down to an altitude of 2,566 meters where he pulled the drag chute. So he had like a 37-kilometer free fall. And figure 1 gives this guy's velocity, angle of attack, the temperature of, so this figure here, the velocity, angle of attack, the temperature of the air, and even the air density with altitude. So we have high altitude on the left, low altitude at the bottom. The black line is the really important one, that's the velocity. Everything else is kind of interesting, but not the key component here. So one thing that is interesting is that he reached his maximum speed quite high up still, so that was at 28 kilometers high. Then after that, he kind of changed his angle of attack, which is given by this red dashed line. So, with all of this gear on Felix, his suit and everything, he weighed a whopping 121 kilos. And interestingly, because Felix jumped from so high, they even had to take into account changes in gravity. So, they have, this is Felix falling down in the sky here. They have this equation here, where they say that gravity at this particular geographic location equals 9.796 minus 3.086 by 10 to the negative 6 times the altitude. So depending on how high it was up, the gravity would be lower, and that's because of how high he jumped from. So we now know how Felix's velocity changed with altitude from his real life experience, but what about calculating it and the drag coefficient? Well, the authors of this paper came up with 3 different approaches. And the first 2 approaches are somewhat dodgy because they take into account don't take into account various values. For example, they assume that the drag coefficient is at a point is assumed to be constant across a certain amount of time, as opposed to taking it continuously. This is method A and method B. In other words, it's kind of like a bad integration where the time space is really coarse, and they don't take into account potentially linear changes in the temperature or density. The third method is better, method C, because it does take into account variations in these properties, but it also is somewhat limited because it assumes that the changes in the air density is linear, but it may not be linear. It may be a little bit different. So these researchers decided to focus more on this third method in this paper, which is the best potential to get a accurate model to be able to predict the drag and the velocity that you'll be traveling at very high speed, at very high altitudes and speeds. So in figure 4, we have a cool plot showing how this drag coefficient changed with Mach number as calculated with this third method. So these are the blue crosses and the red circles, and then we have the line of best fit, which is the black dashed line. So one thing that is really surprising is that the drag coefficient in the transonic region is very low, so between like 0.8 to 1.2. So we do quite a lot of fun simulations on our YouTube channel, and most objects, particularly bluff bodies, which Felix was, get transonic and supersonic drag coefficients between about 1.5 and 4. Felix, on the other hand, was getting drag coefficients of around 0.5 to 1, which is way less. In fact, we all know that as an object approaches the speed of sound, its drag will increase dramatically. But this isn't the case much here for Felix, and we'll go into why that is in a second. But we can see in figure 4 here that when he was only at a Mach number of 0.3, his drag coefficient was about 0.6. So the increase when he went to sonic was not that much. He went to 0.75. And when you pass the sound barrier, your drag coefficient starts to drop, and quite a bit. Felix's did drop, but not that much, maybe by about 10%. And on this graph, they also put the drag coefficient of a rotating cube as reference through this range of speeds. And Horner is a really good textbook from like the 70s and 80s, and it's got a lot of fundamental stuff in there, so I recommend that textbook quite a lot. It comes from this textbook, this rotating cube drag coefficient through this Mach number range. So this cube definitely sees a dramatic increase in the drag, going from about 0.65 at Mach number 0.3 to about 1.4 at a Mach number of 1.1. So Felix is definitely more aerodynamic than a rotating cube. And these authors were pretty good sports, because they acknowledged that there is potential some error in the angle of attack that they measured, and that might affect the drag coefficient that they calculated here. And as such, they varied the drag coefficient by about up to 20% and recalculated the drag coefficients through this range. This is in the AOA uncertainty. Now in figure 5, which I'll zoom out a little bit so we can see the entire thing. Okay, that's good enough, I think. We can see the drag coefficient plotted and calculated with this 20% random error in the angle of attack now, and how that affected the drag coefficient. So the top 2 plots were for the first 2 methods, which aren't as accurate, but they still gave pretty similar drag coefficients to the third method here, which is seen in the bottom plot. So maybe these ones are fairly acceptable still, at least not as bad as we're led to believe. And with this approach, the minimum drag coefficients calculated are actually slightly lower and dipping below 0.5 in some cases, whereas when we don't take into account the potential error in the angle attack, the drag coefficient was above 0.5. So this made a bit of a change here. And a human with a drag coefficient below 0.5 and a Mach number of 1 is shocking. Now, did you get it? Shocking because there's a shockwave. But anyway, it is still hard to believe as it is. And on the other hand, the maximum drag coefficients seen are not that different with the angle attack errors inputted. So we're still getting around 1, a little bit lower than 1. We get a few outliers, but they're mostly within the same kind of range. So one thing that didn't happen to Felix was that he didn't experience a drag crisis. So drag crises are very normal for bluff bodies, and what this is that when you have a bluff body at low Reynolds numbers, the flow is quite laminar. That means that the fluid traveling close to the wall, the inner boundary layer, is quite slow. As such, it is much easier for this boundary layer to separate, and it does. This results in a high pressure drag and total drag overall, because much of the body is in a separated flow now, and more importantly, the back portion, which is where this low pressure occurs, and this results in a high pressure to low pressure deficit upstream to downstream, and that's the pressure drag that we get. Well, when you increase the drag of the bluff body, the boundary layer becomes more turbulent, and that makes the flow near the wall faster. This faster moving flow can resist separation much better. As such, the flow stays attached much longer, and less of the object is in the separated flow. This means that the pressure drag drops and the total drag drops as well with it, because pressure drag is often like the dominant component of drag for a bluff body, and particularly if it's below transonic speeds. So this sudden drop in drag is known as the drag crisis. Well, Felix didn't experience a drag crisis, surprisingly. We see that it's fairly constant and it wiggles around a little bit, but it's pretty good. So the authors attribute this to the fact that while Felix was bluff, because his suits had quite a few folds in it, this turbulated the flow, and as such, even at low Reynolds numbers and velocities, the flow was already turbulent from these folds, the flow going over it and getting turbulated, and as such, the flow stayed attached better. So this phenomenon is known as tripping the boundary layer. So even at lower Reynolds numbers, you have made the boundary layer turbulent. So this is potentially why Felix didn't experience this increase in drag, and a drop in drag with this drag crisis. And we can see down below, we have the Reynolds number plotted with time. Like we can see over his altitude and time, that it did increase a lot, and it went through this Reynolds number range that would often see this drag crisis occurring. So Felix was definitely in the right conditions, but because of his suit, he didn't have to experience this sudden drop in drag, which would have resulted in a sudden increase in acceleration as well, and it would have zoomed off much faster than what he initially was. So another thing we should talk about is the wave drag that Felix experienced. So for many objects, when you reach the critical Mach number, which is when you have sonic flow first forming over your object, you experience a significant rise in drag. This is predominantly due to wave drag, in addition to the shock wave, which is a very high pressure upstream of the object. There is also low pressure downstream of the shock, because straight after the shock, the boundary layer separates. And this results in even more drag. But once you push faster than this critical Mach number, the shock starts to stabilize ahead of the object, and the boundary layer returns to being attached. This results in a drop in the drag, which is why we see the dramatic increase in drag as we approach the sonic flow, and then drops off later. Felix didn't see that as much as maybe expected, and this is because he's a bluff body, so I think maybe he should be seeing this a lot. But because he's a bluff body and so bluff, the pressure drag was already so high and dominant that there wasn't much more of a pressure deficit to elicit. So for airplanes, for example, because they are very streamlined, pressure drag isn't that high. It's not often the dominating component of drag. So we can get a higher drag from this pressure deficit than if we had a bluff body to begin with, and a bluff body as bluff as a human. But one thing Felix did do is create the signature N wave in the shock pattern. So this is where you have two shocks, one just ahead of the object and one just downstream. So the one upstream, we all know, forms because you have the object coming through and that's pushing the air and that's where the shock wave occurs. But the one downstream, that's interesting. Why would that form? Well, the reason why it forms is because you have this sudden change in geometry, and that results in a sudden change, like a change in the velocity, and that can trigger a secondary wave. And this is known as the N wave, which is why we get double booms from traditional supersonic aircraft. Like the aircraft will go by, you hear one boom, and then quite quickly after it, you hear another boom. That's one from the leading, like the start of the aircraft, and one from the tail of the aircraft. So Felix, despite not being an aircraft, still performed this quite vividly. So that's pretty cool. And with that shocking revelation, we reached the end of this podcast. I really like this podcast, and as an avid jumper off things, I enjoyed seeing how jumping from a really high altitude affected the drag of a human. And if you enjoyed this podcast as well, hit the like button. And if you want to see more like this, click the subscribe button or the follow button, whichever platform you are listening to this on. And if you want to get better at CFD, check out our courses in the link in the description. We have a beginner and intermediate course, as well as one for OpenFOAM, which takes you literally all the way from the very basics, like how to install it on your computer and how to type in commands and all that stuff, all the way to running your own complex simulations and processing the results. So from the very beginning to the final bit where you actually get useful data. And in my opinion, it's the best OpenFOAM course out there. And you even get a certificate from us so you can show potential employers. And that makes you a lot more attractive to them. So OpenFOAM is one of the 4 biggest CFD softwares in the world, and arguably the top 2. So it's a big deal. And you can find that course in the link in the description as well. And if you want to make your experiments 2 to 4% more accurate, get yourself Atmosphere Hawk. It's the instrument I was talking about earlier, where the reason why it's an important instrument to have in all wind tunnels is that it measures the atmospheric properties of the air in your wind tunnel. So that's important because it gives you the density of the air in your experiments. And you need to do that because the density of air changes every day between 2% and 4%, and up to 15% throughout the year, like between summer and winter, and rainy and stormy to fine and sunny. So imagine doing a wind tunnel experiment and not even actually knowing what the wind speed is in your wind tunnel. That is what most aerodynamicists are like, because even though they think their wind speed is a certain value, they haven't taken into account the actual density of the air, so their calculation is wrong, as is their Reynolds number. So imagine not knowing what something as fundamental as the Reynolds number of your experiments is. That's pretty funny. But the problems don't stop there either, because when you try to use the data you get from your experiments to validate your CFD, it won't work too well either. And that is a problem that many aerodynamicists face. They check their CFD with their experimental results to validate it, and they see that their CFD is off, and they naturally think, oh, that's the CFD that's wrong. When in fact, it's actually their CFD or their experiments. Both are either right or both are either wrong, or one's right, one's wrong. We don't really know. But because they don't have the density of air the same, we can't really tell. So get yourself an Atmosphere Hawk. It gets rid of those errors for you. And you can find that in the link in the description. And I'll see you next podcast. Peace out, amigos.